السلام عليكم ورحمة الله، يعطيكم العافية جميعا شباب وصبايا، كل عام وأنتم بخير. يا رب ينعاد علينا الجميع بالصحة والعافية. اليوم رح نكمل بموضوع the second law of thermodynamics. Here we will talk about the reversible and irreversible processes. Let's define first what do we mean by reversible process and irreversible process. The reversible process is the process that can be reversed without leaving any trace on the surroundings. While the irreversible process is the opposite. It's simply the process that's not reversible, which means that it's a process that it also can be reversed, but with leaving trace on the surroundings. That's the difference between the reversible and irreversible process. All the processes occurring in nature are irreversible. Let's be clear about this point. Why are we interested in reversible processes? First, they are easy to analyze and they serve as idealized models, theoretical limits to which the actual processes can be compared. So they are idealized, so we want to see how far are we or how close are we compared to these idealized models. So it gives us the theoretical limits. Some processes are more irreversible than others. We try to approximate the reversible processes. In order, as we mentioned, to compare with these idealized models. Now, here to show the differences between how the reversible process behave and how the irreversible process behave, let's check this example of expansion and compression. If we look at the expansion, if it's slow reversible process, we will see that with the expansion, comparing how the pressure distribution will be compared if we have it irreversible. So the pressure, and so the work will be maximum, for the output work will be maximum with the reversible process. While in the compression, compare it with the compression with the irreversible process, similar talking can be concluded. So the reversible processes deliver the most work and consume, when we talk about the compression, consume the least work. So they are idealized models. Examples of the reversible processes: frictionless pendulum and quasi-equilibrium expansion and compression of a gas. Now, what caused the process to be irreversible? We call these factors irreversibilities. So the irreversibilities are the factors that cause a process to be irreversible. They include friction, unrestrained expansion, mixing of two fluids, heat transfer across a finite temperature difference, electric resistance, and elastic deformation of solids, and chemical reactions. Those not limited to these. And so the presence of any of these effects renders a process irreversible. So cause the process to be irreversible. So here it shows the factors that we just mentioned. And besides those factors, the fast compression, the fast expansion, the unrestrained expansion, such as the rupture of a membrane here. So these are also factors, or also irreversibilities. Okay, when can we call the process to be a reversible process? It must be both internally and externally reversible. What do we mean by the internally reversible process? If no reversibilities occur within the boundaries of the system during the process, we call it internally reversible process. Example of the internally reversible process: if we look at this piston cylinder device, which is a closed system, as you all know from the previous topics we studied. So if the heat transfer into the piston cylinder device, we have the system inside the cylinder at 20 Celsius degrees, okay? So we can see that the system is in thermal equilibrium, okay? And so it's internally reversible. There are no irreversibilities within the system, So the system, while the externally irreversible, that's when there are no irreversibilities occur outside the boundaries of the system. So here, okay, if the outside, the surroundings are at 30 Celsius degrees, we can see that there is a finite temperature difference, or it's a heat transfer, okay, it's a heat transfer of finite temperature difference, 30 Celsius degrees, 20 Celsius degrees, delta T is finite. And this is, as in the previous slide, we mentioned that the heat transfer across a finite temperature difference is one of the irreversibilities. So that's why this system here, B, is considered as just internal reversible, not external reversible. So it's not totally reversible, and so it's not reversible. The totally reversible process, it involves no reversibilities within the system or its surroundings, such as here. We can see the surroundings is at temperature, which is 20.000. So we can see that the temperature difference between the system and the surroundings is not finite, and so there are no irreversibilities outside the boundaries of the system, and so it's both internally and externally reversible, and so we can call this process as totally reversible process. Okay, so a total reversible process involves no heat transfer through a finite temperature difference, no non-quasi equilibrium changes, and no friction or other dissipative effects. The Carnot cycle. Since we mentioned the reversible processes and irreversible processes, we come to the reversible cycle. As we know, the cycle consists of it's a process that the initial and final states are identical. The reversible cycle, and we take an example of the reversible cycle, the Carnot cycle, consists of several processes. Here there are 4 processes, which all are reversible processes. Starting from process 1 to 2, that's considered a reversible isothermal expansion. Okay, we can see the piston cylinder device, initially the system at temperature T sub h. The heat transfer into the system from thermal energy reservoir, which is also at T sub h, and with the amount of Q sub h. So this is considered as a reversible isothermal expansion process. The temperature remains constant through this process. Now, the second reversible process is also expansion, but under adiabatic conditions. So it's considered as reversible adiabatic expansion. That's process 2 to 3. And here the temperature reduces from T sub h to T sub L during this process. Okay, now the third process is the reversible isothermal compression. Now it's compressed because we want to go back to our initial state, so we need compression processes now. First, it's an isothermal compression process. The heat is transferred to at an energy sink, which is at T sub L, and the process is under constant temperature T sub L. The last process in the Carnot cycle is the reversible adiabatic compression. So under adiabatic conditions, the process goes now from 4 to 1. From 4 to 1, so we return back to our initial state, and this occurs through temperature increase from T sub L back to T sub H, back to T sub H. So this is simply the Carnot cycle, consists of two reversible isothermal processes and two reversible adiabatic processes. This can be shown on the PV diagram as shown here to the left. This represents the PV diagram of the Carnot cycle. This Carnot cycle occurs in devices such as the heat engines, where we will have net output work. The reversed Carnot cycle is what also known as the Carnot refrigeration cycle. The Carnot refrigeration cycle, it occurs in consuming power devices such as the refrigerators, where we will have net input work in this case. Here it shows the processes as described in the previous slide in both these figures. Those figures are very important figures. Okay, we come now to the Carnot principles. The Carnot principles, simply the Carnot principles tells us that the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. And this is the idea from having these, as we mentioned, these will be as theoretical limits. So we always compare our models to these theoretical limits. So this first principle is described in this sketch here to the left. We can see that the irreversible heat engine, its efficiency will be less than the reversible heat engine, knowing that both are acting between the same two reservoirs. The second Carnot principle is that the efficiencies of all reversible heat engines operating between the same two reservoirs are the same. And that brings us to this conclusion that we will show in a little bit, that we expect that the efficiency of such reversible heat engines will be determined based on a scale that's independent of the properties of the substances. يعني راح يكون بيعتمد على مقياس لدرجة حرارة ما بتعتمد على خصائص المواد. That's why no matter what's the design, what's the working fluid in these reversible heat engines, as long as they operate between the same two reservoirs, they will have the same efficiencies. So those are the two Carnot principles. Here to the right, it shows the proof of the first Carnot principle, that the reversible heat engine will be less, efficiency will be less than the reversible heat engine. Okay, this is part of an example which we will see and solve some examples later. Now, here we will talk about the thermodynamic temperature scale, which we introduced back in back at the beginning of the course. The thermodynamic temperature scale, or the absolute scale, it's a scale that's independent of the properties of the substance. So لا هو مقياس درجة حرارة لا يعتمد على أو مستقل من الخصائص المادة. Okay, here so the thermodynamic temperature scale for the SI units, that's the Kelvin. For the English units, that's the Rankine. Recall here the relation between the Kelvin and the Celsius degrees is shown in this relation here. So the Kelvin scale is the absolute temperature scale for the SI units. Okay. Now, for the reversible, it's introduced. It's proposed that the ratio between the heats, from the hot temperature reservoir and the low temperature reservoir is a function of their corresponding absolute temperature ratios. And what's this proportionality? Simply, it was Kelvin, assumed that it was simply linear as shown here in this relation. So uh, for the reversible cyclic devices, we will always assume that the ratio of the heats is equal to the ratio of their absolute temperatures. Absolute temperatures. The Carnot heat engine. The Carnot heat engine. So based on this fact, now the efficiency, the thermal efficiency of the Carnot heat engine, which is for the actual or any heat engine, it's according to this relation, which we discussed before. And so for the Carnot reversible heat engine, now since the ratio of the heats is equal to the ratio of the absolute temperatures, so for the reversible heat engine also the efficiency is according to this relation. Both relations are valid for the Carnot heat engine, while this relation is only valid for the actual heat engine, which is not Carnot or not reversible heat engine. The facts about the thermal efficiency in general, it's has these three actual two possible options, while the third option is impossible. The first option is to be less than the thermal efficiency of a reversible heat engine, knowing that it acts between the same two thermal reservoirs, and in this case, this heat engine is considered irreversible, or it equals to the thermal efficiency of a reversible heat engine, and in this case, it, according to Carnot principles, it's a reversible heat engine, or it's greater than the thermal efficiency of a reversible heat engine. In this case, it's impossible. And it's always it's one simple way to check let's say the validity or the reality of an invention by of heat engine is always to do this check to check its thermal efficiency and see if it's greater than the thermal efficiency, assuming that this heat engine is reversible. That means this invention is impossible, and it cannot be realistic. The quality of energy. We talked that the second law of thermodynamics gives us indication about the quality of energy as well as the quantity compared with the first law of thermodynamics. It tells us here, if we check this reversible heat engine and compare its high temperature reservoir, we can see as we increase the high temperature, the T sub H, the efficiency of the reversible heat engine will increase. So that means the higher, even though the nothing else have changed, but it tells us that the higher the temperature, the higher the quality. So the higher the temperature of the thermal energy, the higher its quality. Okay. Okay, a simple question for all of you. Can we use Celsius degrees units for the temperature here? No, we cannot, because it's in the absolute scale. Okay. Now the Carnot refrigerator and heat pump. The Carnot refrigerator and heat pump. Similarly, the reversible refrigerator will have the best performance compared with the irreversible ones, knowing that they act between the same two reservoirs. So again, the Kelvin proportionality apply here. Kelvin proportionality applies here. The COP for the refrigerator, as you know from the previous lecture, equals to 1 divided by the heat ratio between the hot temperature and the low temperature, or the high temperature and the low temperature. And while for the heat pump, it's according to this relation. If those refrigerator and heat pump are Carnot or reversible refrigerator or heat pump, then they can also be represented in their temperature ratio, knowing that those temperatures must be in the absolute scale. If we are using SI unit, that means in Kelvin units. Okay. Remember that any refrigerator, it follows these two relations, but only the Carnot or reversible heat pump and refrigerator follow these relations. Okay, here the COP, the coefficient of performance for the refrigerator, and this may also apply to the freezer, the heat pump, the air conditioner. It has these two possible options, while the third option is impossible. It can be less than the COP of a reversible one, or equal, and in this case, this device is irreversible, or equals to the reversible COP. In this case, it's a reversible device, or greater. In this case, it's impossible. It's impossible. Okay. Now, knowing this is from practice, the COPs of both the refrigerators and the heat pump decreases as the T sub L decreases. And that means they require more work to absorb heat from the lower temperature media. And this can be shown from the theoretical limits here. Okay, as the T sub L decreases, okay, the COPs will decrease. Okay, that's all. So we finished this chapter. يعطيكم العافية ونراكم إن شاء الله بالnext lecture. السلام عليكم ورحمة الله وبركاته.